Greetings. We're going to be talking about how to symbolize arguments this evening. Now, we've already looked at some ways of symbolizing or representing arguments. We've looked at various ways of examining and testing for the validity of arguments, but there's a way in which most of these are incomplete. We found out how to construct counterexamples to arguments, which is a nice way of testing for validity. But we didn't find any way that's completely general. The counterexample method, in part, depends on your ingenuity in finding a counterexample. And besides, the fact that you haven't found a counterexample doesn't show for sure that something is valid. The famous forms method shows that something is valid, but not all arguments fit into one or more of the famous forms. When we went to the categorical syllogism, we found that we could state definitely some of those are definitely valid, some of the rest are definitely invalid. In fact, we can classify them completely as to which are valid and which are not. The problem is that not all arguments are categorical syllogisms. What we're going to be doing now, and over the next week this is going to be a pretty easy task, but it's important to get it down and get it right. What we're going to be doing now is we're going to spend some time learning another way of symbolizing arguments, and a way that will enable us to work out a more complete way of representing and showing when an argument is valid and when it is not. We need to start by introducing a few more terms. First, atomic statements. An atomic statement is a statement that does not have any other statement as a part. Here's some examples. Pittsburgh is in Pennsylvania. Eating vegetables is healthy. Snow is white. And the sky is orange. Obviously, an atomic statement doesn't have to be true. The key idea of an atomic statement is that it can't be divided. It comes from the same word as our word atom, which itself comes from an ancient Greek word, atomos, which actually means uncuttable. It was the ancient Greek idea that sooner or later, if you divided things up, you took, say, a chunk of clay and you cut it in two, and you cut it again and again, sooner or later you would get to something that was so small that it couldn't be divided further. It was uncuttable. And that was the word atom, or that was the source of the word atom. An atomic statement is uncuttable. In other words, if you take it apart, you haven't got a statement left at all. You've got pieces of a statement, or parts of a statement, but you haven't got a whole statement. So, an atomic statement is the smallest possible complete statement. Now, going forward, we can consider compound statements. A compound statement has an atomic statement, at least one, as a part, but it is more than just the atomic statement by itself. Here's some examples. It is not the case that the sky is orange. If Pittsburgh is in Pennsylvania, then Pittsburgh is in North America. Notice that has the two atomic statements as part of it. Pittsburgh is in Pennsylvania, and Pittsburgh is in North America. Snow is white, and eating vegetables is healthy. And so on. Those are compound statements. Now, if we want to symbolize these, or symbolize the atomic statements, there's a very easy convention for doing it. Basically, we represent an atomic sentence with a single capital letter for each. For example, we say, use P for Pittsburgh is in Pennsylvania. N for Pittsburgh is in North America. E for eating vegetables is healthy. S for snow is white, and O for the sky is orange. If you do that, what you've done is you've created what we can call a scheme of abbreviation. The scheme of abbreviation is temporary, it's for a particular purpose. You don't need to use the same scheme of abbreviation for everything, and you don't have to come up with ever weirder and more complicated ways of symbolizing things. The point of a scheme of abbreviation is just to get you a set of letters that you can use in symbolizing a particular argument and keeping them consistent during that one argument. Now, if you've got a scheme of abbreviations, then you can start putting these atomic statements together into the compound statement. And representing it in a much briefer way. Instead of, it's not the case that the sky is orange, you can symbolize that, it's not the case that O, because we used O to represent the sky's orange. If Pittsburgh is in Pennsylvania, then Pittsburgh is in North America. We can symbolize that this way. If P, then N. For snow is white and eating vegetables is healthy, we can represent that as S and E. We just connect them in these various ways or comment on them, like the first example, it is not the case that O, or that is, the sky is orange. However, we could go further than this. Once we've got abbreviations for the particular atomic sentences that we're going to include, it may also help to have abbreviations for these other things that we're including. Things like and or, and it is not the case that. And indeed, we do. When you have an atomic statement, there's the question, how do you get from there to a compound statement? The answer is, whether you've got one atomic statement or several, what you need to connect them together and produce a compound statement is some kind of logical operator. And we've got symbols for the various logical operators that we'll be working with. Now this chart is basically the same as one that's in your textbook near the top of page 279. I've got like one or two changes, and I'll mention them briefly. Where the textbook says type of compound, I've got type of operation. I think that's a little bit clearer. And second, this is also not very important, but the V symbol for or, they say that the name of that is V. It's also sometimes just called the vel symbol, which comes from a Latin word for or. In any case, there's not much to say about this. These operators, however, are what allow us to put together compound statements. And we're going to look at them in a little bit more detail. Look at each one of them, beginning with negation. Now, the symbol for negation is the tilde. And the basic idea of negation is just to say it is not the case that something. There are various stylistic variants on this. For example, it is not true that whatever it is. Or, it is false that. And of course there are other ways to do that in English. But the basic idea of negation is that it takes whatever content is already there and it denies it. It says, whatever that is, it's not so. That's the basic idea of negation. And negation is, in a certain sense, the simplest form of creating a compound statement, because you can have a single atomic statement and then its negation makes it a compound statement. You say, Alice wants to go to the party. That's your atomic statement. It's not true that Alice wants to go to the party. You've still only got one atomic statement as part of that, and then you've got something else. It's not true that Alice wants to go to the party. That's negation. Turning now to in the next symbol. Maybe you can barely see it there. It's the dot symbol, and this stands for conjunction or and. And again, there are different ways to represent this in English. The most obvious, of course, is just and. Another one, not quite so obvious, is but. Now you might think there's a sort of a meaning or a shade of meaning when you say, there's a difference when you say Joan is going to the party and she's unhappy, and Joan is going to the party but she's unhappy. There's a suggested difference in meaning there. However, for our purposes, these can both be represented as conjunction. They're ways of putting these two sentences together, or these two statements together, and making a compound statement out of them. Another possibility might be while. When you say, well, one thing's true while another is true, that's another case of conjunction. Again, you've got to get used to these various stylistic variants so that you can substitute them. But conjunction is the basic form, the and symbol. Now it's time to take a look at disjunction. This is the operator that refers to or. It's called the V or the vel operator. And of course it stands for putting an or in between two statements, two atomic statements, and sometimes an and or between two atomic statements. Another possibility is sometimes an unless between two statements. Martha will go to the party unless she's busy. That tells you either she's at the party or she's busy. Now, one important note, which we have discussed a little bit on the discussion forum, is that for the purposes of logic, we use the inclusive or. The inclusive or means that if you've got two things, say A and B, and you say A or B, it means one of them is true, or the other one is true, or they're both true. That's the inclusive or. Now sometimes people use, for lots of purposes, what we can call an exclusive or. An exclusive or says one of them is true, or the other is true, but not both. And sometimes it's not completely clear which you mean. Or sometimes it is completely clear and people find it odd that logicians use only this inclusive or. Well, there is a reason for it. Actually, there's a couple of reasons for it. The first reason is that almost everything that you want to do with an or statement can be done with the inclusive or. You can almost always do what you want when you've got either it's in my left pocket or it's in my right pocket. Well, you might think that's an exclusive or. But the only use for a statement like, well, my wallet's either in my left pocket or it's in my right pocket, is then to add another premise like, well, it's not in my right pocket, therefore it must be in my left pocket. And you can do that whether it's an inclusive or an exclusive or. So it doesn't make any difference. For most purposes, an inclusive or will do all the work that you want to do. But occasionally you may want to use an exclusive or. And there's an easy way to handle that. You just add an extra clause. And then you have an exclusive or built out of an inclusive or. You say, either it's in my left pocket or my right pocket. I don't know if I can do this with a wallet. Well, maybe I can. I say, either it's in my left pocket or it's in my right pocket, but not both. I I can add an extra clause to say, but not both. And that gives you the exclusive or. Anyhow, that's the basics of disjunction. And you'll have to learn, of course, some various stylistic variants, but you're familiar with those. Now we move on to conditionals. For this, we use the arrow symbol. These are the familiar form if-then that we've already encountered in modus ponens and modus tollens and so on. And there are different things that you can use here, different stylistic variants, but there's not any real point in saying a lot about them at this point. You should be familiar with these by now. The only important new point is that we're using the arrow to represent this. Last, we're going to talk about biconditionals. For this we use the double arrow, and the biconditional stands for if and only if, or sometimes for just in case. And this says, well, if one is true just in case something else is true. That's an example of a biconditional. And another one might be something like, one thing is a necessary and sufficient condition for another. Those are different ways of expressing the biconditional. It's called a biconditional because basically it comes from putting together two conditionals. Suppose you have two statements. Let's call them A and B. And you have if A, then B. If you add to that, if B, then A. And you say, if A, then B, and if B, then A. That's equivalent to the biconditional. Whenever both of those are true, you've got a true biconditional. Anyhow, that's the meaning of a biconditional, an if and only if statement. I'm going to introduce a further concept. This is the idea of a well-formed formula, or a WFF. Now, a well-formed formula is a way of adding a little bit of additional precision to the way that we represent these things. We've got the atomic statements, which can be represented by capital letters. We've got compound statements, which can be represented with the capital letters plus various operators. But how exactly do these get put together? Well, that's what this is supposed to tell you. It's supposed to be a technical way of making it precise exactly how you can put together operators and atomic statements. And what you get is, first of all, we have basically a simple set of rules. A capital letter, a single capital letter, is a well-formed formula, or a WFF. Second rule, if P, and P is something that represents a statement, either a simple atomic statement or a compound statement, it just represents any such statement. And we'll introduce another one to do the same thing later, which we'll call Q. If P is a well-formed formula, or WFF, then so is not P. If P and Q are well-formed formulas, then so is this expression, where we've got P and Q together in closed parentheses. If P and Q are WFFs, then so is P or Q, again in parentheses. If P and Q are WFFs, then so is if P then Q. And last, if P and Q are WFFs, then so is P if and only if Q. And that's it. Those are all the rules for well-formed formulas. Now, in a way, this is what we've been talking about today. What we've been talking about this evening is fairly simple, and it's straightforward, and it's not complicated. It is important, however, to understand it, to absorb it, to imprint it on your mind so that we can start using it starting with our next reading, which I believe will not be until after your spring break. But for right now, the important thing is to get used to these and get used to the way that you can use these to symbolize arguments in English. This will lead to a much more powerful way of representing arguments and representing when they are valid and when they are not. And for tonight, that's all.